So let us just do it, and people, maybe others will come. I know that some of them told me they will come a bit later. So, okay, so last time we discussed the situation that you have this smooth variety given as a zero section of a bundle. And its a virtual class of our smooth variety was given by fundamental cycle of it capped with top churn class of the bundle that this thing was the zero locus of. Okay, now let's discuss more general cases. In particular, let us discuss more about virtual fundamental class. Hopefully we can see two constructions of it today, and we can also see an example of how to compute it also today. So now first let's do a little bit classical stuff. So recall from Kuranishi theory, that for a complex manifold, let's call that M, the infinitesimal deformations are governed by this group H1 of M, H1 over M of its tangent bundle. This is what Kuranishi theory tells us. And the obstructions are governed by H2 on M of the tangent bundle. So this is what Kuranishi theory tells us. Then Kuranishi theory describes the moduli space of M, the moduli space of M as the zero locus, of holomorphic obstruction map. So zero locus of the holomorphic obstruction map, which I'm going to write as some map from U to H2 over M of tangent bundle, and this U is inside, it lives inside H1 of Tm as a subgroup, as an open. And of course, these groups, you can give them the vector space. You can think of them vector spaces over C. So this could be as well a subspace of H1. So this is the deformation. It's a group, but you can also make it into a complex vector space over C, and you can think of it as a space. And this is an open subspace of this thing. This then can make sense to have this map as a holomorphic map from here to here. Okay, so roughly speaking, looking at the map, you can see that the moduli space of M is realized as zero locus of this map. So where the obstructions vanish, the M is realized as some subspace of tangent deformation. It's deformation space. Okay. Okay. Now, from this description, the expected dimension of M is just dimension of the H1 minus H2. So dimension of this H1 minus dimension of H2 that I put over there. Okay. Now for M bar GNX beta, the reasoning would be similar. So for instance, let us look at a map from a pointed to stable map from a pointed curve into the ambient variety. So let F be a map from a pointed curve. Remember that again, stable map doesn't mean a stable curve. The curve could as well be unstable, and there is a map from the moduli space with stable maps to moduli space with stable curves, which is given by contracting unstable components. So let's say we have a stable map from a pointed curve into the ambient variety X. So let this be a stable map. Okay. Then we can define what is the tangent space to this moduli space at a given point, at a given map. So the tangent space at this point, represented by this map of the moduli space, is given by x1 pullback of the shift of differentials or the tangent bundle of x to shift of differentials of C or the canonical twisted by these mark points as divisors. So twisted by the divisor defined by the smooth mark points. And this X group is computed on C, and this is the hyper X group. So you compute this using the injective resolution or projective resolution, the way that hyper X are defined. Okay, so this is the tangent space. It's a group, but also as a C vector space, it's a space. So it's a space. It's a tangent space to the moduli space. And the obstructions live in this other X group. Obviously, you can expect what this is. This is the hyper X2 group. Omega C twisted by the divisors of C. Okay? Again, hyper X group. Now, of course, the expected dimension of the moduli space expects the dimension of M bar Gn X beta is the dimension of this X1 hyper X group minus dimension of this guy X2. And without proof, we have actually shown what is the expected dimension. We had this last time. What's this expected dimension? But now we can actually prove it, because now we know from Quantum theory the moduli space is realized as a zero locus of the obstruction map between these two spaces. So all we need to do is finding some way of calculating this minus that. And that we can do by looking at the long exact sequence of cohomologies that exist naturally for this problem. So there are many different ways of seeing it. So for instance, let me call this thing I dot. So this is a hyper X group from a complex on C to structure sheaf of C. And so what is this complex? This complex is exactly this complex, and this could sit in degree -1 and 0. So basically, you can see that naturally there is this exact triangle. Goes to that, and we are just calculating dimension of x1 of I dot comma OC minus dimension of x2 I dot comma OC. But now from this exact triangle, you can actually compute the long exact sequence of cohomologies. So for instance, you can easily see that by applying Arham OC to that thing, you can easily see that there is a map from x0 I dot OC to x0 omega C pi OC. So x0 pullback of the canonical pullback of the differentials of x to OC. Okay. And then you can have a map from here to x1 I dot OC, x1, and then x1 again. So that, and then you can finally get a map to x2 I dot comma OC. And so what's the next term?
Doesn't exist.
Doesn't exist. Excellent, because the curve is one-dimensional and these are just sheaves. So goes away by Kodaira type vanishing. Okay, so what is it that we are doing? We are discussing that. We discussed the Konishi map. So let me just summarize. We were just talking about the following, since you came a little bit later. We're talking about the Konishi map. So every manifold that you have, the Konishi theory tells you that the moduli space of such manifold lives as the zero locus of the following map. So you look at H1 of tangent bundle to H2. This is the obstruction space, and this is the deformation space. Of course, the Konishi map tells you that actually Konishi holomorphic map is from an open subset in here into here. And so expected dimension of your manifold, the moduli space of your manifold, is given as the dimension of this guy minus this guy, dimension of this minus that, right? That's what we are trying to do. Now, we are replacing our manifold with the moduli space, but then the reasoning is the same, and all we need to do, we just realize the tangent and obstruction space at the given point of the moduli space. Basically, this group, or vector space over complex numbers, and this one. We know that these are identified by x1, pullback of the differentials of x to omega c, and this is a hyper-x group. So x1 and x2 of this. We think of this as a complex, and we are calculating the hyper-x group of a complex to OC on the curve. So this is the obstruction space, and the deformation space is given by x1. So how do we calculate dimension of x1 of Ham I dot OC minus x2, h1 and h2 of these two Arham sheaves? We are of course calculating that using the long exact sequence of cohomologies. Why is that? How can we calculate it? Well, this is I dot, it sits in an exact triangle, and I can apply Arham over curve, comma OC to it. So that's what we are doing. Okay. Now, let's discuss some interesting things in here. So, for instance, what is this thing? You can actually see what this is. If you dualize this using some sort of, you think about Serre duality on the curve. If you dualize it, then that gives you deformation space of the curve while the curve is fixed. It's a normal bundle, we know that from Hartshort. Because this is the pullback of the cotangent bundle, but dually it's the pullback of the normal, the ambient tangent bundle, which is the normal bundle. So this is the space of infinitesimal, first order doesn't matter. First order deformations of the map F with the curve C fixed, because we are calculating on one curve, obviously. Okay. Now, the term before this, now this is not pullback of anything. This is, if you use stereotype or anything, you can actually see that this is just infinitesimal automorphisms of the curve, right? So this is just space of infinitesimal autos of the curve. Together with these, of course. It sees these divisors. And why do the space of infinitesimal autos exist? Well, because this could exist, right? Because the map could not have infinitesimal autos, but have finite autos only. But the curve need not be stable. So this could exist since C, the data, this can be unstable. So it can have non-finite autos. Okay, good. So let me call this map something mu. Okay, but then the fact by stability of F, we can actually see that this map needs to be injected, right? Because the map F doesn't have infinitesimal automorphism, so by stability of this map, of the map F, mu is seen to be injective. Thus, x0 I dot OC is equal to 0. Okay, so that piece is equal to 0. This goes away. See, up to here, logical resilience, log exact sequence of cohomology, but here is just looking at what exactly geometrically these group govern. So this is equal to 0. And now I can calculate. So we can just see that. So let's write that down. You can see that dimension of, let us define x as the dimension of x. Okay, so x0 r dot OC, which is equal to 0, minus x0 omega pi's OC plus x0 like that, minus x1 and then there is this x2 obstruction space, and then there is x1 there is nothing in here. And then there is this part. Okay, so this whole thing is equal to 0. So from here, if you just look at the difference of these two, put it on the other side. This is minus the expected dimension. Put it on the other side. You can see that then the expected dimension of M, by Carnot theory, the expected dimension of the difference of these, is going to be equal to Euler characteristic of the pullback of the tangent bundle plus x1 of omega c twisted by pi's and O minus x0 omega c twisted by same thing. This is coming from these two, obviously. It's a curve, so all the characteristics has only 1 and 0. x0 and x1, so that's what it is. Okay. Okay, so you have this thing, and so x1 minus x0. So what is this again? This we discussed. So this is the infinitesimal autos. So this is the infinitesimal autos of the curve, right? The second bit. And this is the infinitesimal deformations. Right? So let's just write it this. So this is the first order. So I write it by red. First order deformations of the curve. So this should be the dimension of the tangent space to the moduli space of curves, this bit. So then we can see that expected dimension of the M bar GNX beta is equal to Euler characteristic of pullback of tangent bundle plus the dimension of tangent space of M bar Gn. Because M bar Gn, it's equal to that. M bar Gn basically is constructed by rigidifying those curves by looking at the finite automorphism. So the scheme, there is a group scheme on the moduli space of all curves, which actually is the group of automorphism you mod out by that, by in the sense of GIT. So that's what your moduli space is. Then you can actually see that the deformation space at the point minus the group that governs the infinitesimal autos gives you the dimension of the tangent space to moduli space of stable curves by construction. Okay? And, well, this is equal to 3, we discussed this thing, 3g minus 3 plus n. And, well, this is just by growth and decree Monrock. This is just, you can calculate it by this formula. This bit. So this is by okay, so this is the formula we had before. Okay, any questions so far? All right. Now let's discuss. So this is just some. So far we know there exists something like a virtual class. It's an element of cohomology of the space. In this case, for us, it's going to be the moduli space. It sits in a particular degree of this graded ring, and the degree is equal to expected dimension. And the expected dimension we can calculate by thinking of the moduli space via Konishi theory, and this was the calculation for it. Now, let us go back to formal construction of virtual classes. We are going to construct a class in the cohomology of the moduli space which sits exactly in the degree equal to this number. So formal construction of virtual fundamental class, VFC. Okay, so let us define a functor. Let F from category of schemes over complex numbers to sets be a contravariant moduli functor. We discussed this thing last time. So what does it do? It takes a C scheme 2 of the set of isomorphism classes of S flat families, S flat families, or families of certain geometric objects, flat over S flat families of objects of fixed given numerical type. Okay? So objects of fixed given numerical type. For instance, for us, could be the genus or the homology class of the curves or maps, the stale maps. For the sheaf moduli spaces, it's going to be the Chern character or the Hilbert polynomial and things like that. Okay, so you have a moduli functor right, like that. Then let us for now assume that S is an affine scheme. Assume that S is affine. Now we are going to construct something called tangent obstruction functor associated to this functor F. And for that, this tangent obstruction functor, roughly speaking, and it is good actually to mention this before going through the real abstract construction, tangent obstruction functor just understands the kind of how does this, what happens to these families when you deform the underlying scheme? When you extend the underlying scheme, what happens to the image of this functor? So the tangent obstruction functor eventually produces for you some object in the derived category of some space if the functor, here the moduli functor, is represented by some scheme. So tangent obstruction functor induces the tangent obstruction complex on the space representing this functor, or the moduli space. The fiber of this tangent obstruction complex understands deformations and obstructions to those deformations at points being parameterized by the moduli functor. So that's what it is. Okay. Now, formally speaking, you take a scheme, and I want to construct this tangent obstruction functor. So let S be an affine scheme, and let S inside S of n be an infinitesimal extension of S by some via or induced by some OS module n. What is that supposed to mean? That is S is the affine spectrum of OS plus n. So I'm sure looking at Harshon and so on, you're familiar with this thing. So imagine that your n is an ideal. Let's say it's a square zero ideal. If it's a square zero ideal, this here is an ideal in here, but then it will be an OS module, an ideal as well. And point-wise, we can actually see that this could be also split. Okay, so, but, this is more general than that. So, let's say that we have some extension like that, induced by an OS module, then naturally, okay, so this is such that obviously this extension has the property that if I embed, natural embedding is given this way, then natural projection by restriction back to S is induced. So if I look at this thing, this map should be identity. Okay. So let's say we have something like that. Now we can define some projection pi of n from F of Sn, which is the isomorphism classes of objects, families of objects parameterized by S of n, which after restriction to S gives us isomorphism classes of families of objects parameterized by S, flat over S of n and flat over S. Okay, then the tangent functor Tf of F, tangent functor Tf of F is defined as follows. So if I want to tell you what's the tangent functor, I need to tell you what does it do to elements of the category of schemes over complex numbers. So for S in schemes over complex numbers, like that, and some element alpha in F of S, let's say alpha is the representative of an S-flat families of objects parameterized by S, then tangent functor of alpha, tangent functor evaluated at alpha, gives us a map from OS modules to sets. And what is this map? This map takes us, okay, so let's write it like this. Tangent functor of alpha, it needs to depend on this module n. So tangent module of alpha defined for the OS module n, like that, takes us from OS modules to sets, and the map is given by the map that takes n to the isomorphism class, or the set of elements of pi n inverse of alpha. And pi of n is this. Let's look at this for a while. So this is what this tangent functor does. It is something that understands the perturbation in the families being parameterized by these schemes as soon as you perturb your scheme. So, but of course, it also has another description, which I can put this bit into words. So I can say that this tangent functor of alpha, f of alpha, for this module n, gives us a set of isomorphism classes. Isomorphism classes of all elements in f of Sn, all elements in f of Sn which are in the image, pre-image of alpha, right? Alpha that's in here. All elements of f of Sn which whose restriction to S is alpha. So for instance, if this was the functor, the moduli functor that defines the moduli space of sheaves, the functor takes you from schemes over complex numbers to flat families of sheaves. You perturb your scheme by some module, let's say square zero ideal or whatever else you can choose. And then f of Sn, tangent functor basically gives you a map from the ideal or that module that you use to define the extension to flat families of sheaves whose restriction to the original scheme is the original flat family. The same for maps and same for curves. Okay. Yes, so now we can also associate to a tangent functor what is called a tangent obstruction complex. Tangent obstruction complex. It's written this way. This is the notation for it. Okay? So this is the tangent functor of f. Understands, again, how the families see the perturbations in the underlying schemes. And this is the obstruction theory of F. This gives obstruction theory. And when your functor is represented by a scheme, this naturally gives you tangent obstruction complex on that scheme. Fiber-wise on the points of the scheme, this gives you first-order deformations, and this gives you obstruction fields. Okay, for instance, as an example, when Sn is a square zero extension of S by some ideal n, like how I put it before, then associated to the data of alpha, S, and N. Alpha is one of those S-flat families. We can define an obstruction class. We can define an obstruction class. Which lives in who's vanishing, just the class of that group is vanishing, or the class associated to that group. Is necessary and sufficient for the existence of an element. Let's call that element alpha bar in f of s of n extending alpha. Okay. Now, of course, when we get back to moduli spaces right away, in some couple of minutes, and you will see what is the obstruction class for the moduli space of stable maps or sheaves. Think about moduli space of sheaves, even though we are not going to do much of it for now, but in the middle of the spring we will be over moduli space of sheaves all over. So this kind of thing, the moduli functor defining the moduli scheme, the coarse moduli space of sheaves, comes with a tangent obstruction complex like that, and it is some complex in the derived category of the moduli space. This term, it's a complex of vector bundles whose first cohomology is x1 f comma f, second cohomology is x2 f comma f. And the obstruction class is always x2 f comma f, tensor with the ideal with which you are deforming the thing. So this ideal is always there, right? And of course, if you look at Hartshorne's deformation theory notes, or Eduardo Cernesi, and so on, these are good sources, you can see.
I asked how different is this extension by n with the square zero extension by ideal? Is it just that it's not square zero? But
Yes, that's it. Yes, that's right. That's more general. Yes, that's right. That's it. But it's a good example of a square zero extension for our purposes. Okay. So this is that, and then now let's define this. I told you that when the moduli space is represented by some scheme, we have the tangent obstruction complex. So definition, this will be definition 8, I think. A tangent obstruction complex is perfect if for each piece of data alpha and S there exists, well, at least locally on S, a two-term complex of locally free sheaves of OS modules. Let's call these things E1 goes to E2, such that for any n, the ti's, the tangent functors of f of alpha induced by the OS module n is the ith sheaf cohomology. Ith sheaf cohomology of this complex E dot tensor with n. Over OS. It's a complex of OS modules, so in fact, so it does make sense to drive tensor it with O of S. And since these are locally free sheaves, yes, so they're like bundles. I mean, locally free sheaves, at least locally honest. So it does make sense to think about this. Now again, think about that Arhan complex, which captures deformations, first order deformations, and obstructions to those deformations of moduli functor of moduli space of sheaves. Here is X1. F comma F. This is on S, right? So sheaves which are defined by, S flat sheaves in here. And okay, so if you have a moduli functor, by the universality property of this thing, every time you pick a scheme, you look at the image of the functor, it gives you an S flat families of sheaves. So let's call that S flat family F of S. Okay, so this would have something like x1 f of s comma f of s, x2 f of s comma f of s, and then you can tensor those with the ideal with respect to which you're extending your sheaf. So the deformation space and the obstruction spaces are always given by x1 f comma f tensor with the ideal and x2 f comma tensor with the ideal. So you have seen this before. Okay. All right. So now, so now let's do this an example. Now let's define as. Remember that I used the curly mg and x beta to distinguish between the moduli functor and the moduli scheme. The tangent obstruction complex for this data is given by so we just use the same notation we had before. So this is T1 of m bar gnx beta, T2 curly m bar gnx beta. Okay, and these are going to be so we would like this, so let's look at the definition. So we would like these TIs evaluated at some alpha and some ideal to be ith cohomology sheaves of some complex tensor with I, right? So we would like, so these are going to be for us the things that we defined before, but remember that now we are working over this flat family, over this scheme. So x1 C over S of pullback of the differential sheaf of differentials to omega C over S twisted by some divisor D O of C N and X2. I'm writing it in a bad way, but you should remember that basically what I'm trying to say is that there is some Arham complex, okay, over the universal curve over this S, right? So remember that you're embedding this over here. So then over here, there's a universal curve, like that, whose fiber over every point of S gives me one of these C's inside X. So that's that. So this also I'm notating like that, the universal curve on S. Then there's also a, for every time that S is a point, I have points inside curve, points on the curve, n marked points, n sections. So same here, I can have n sections on this thing. And for I1, I2, I can have PI1 to PIN. And so the union of these PINs from 1 to n, I call it D. These are the section maps to the curve on X, to the universal curve on X cross S. Okay. Then on the derived category of this curve, which I denote by C over S, the curve on S, we can have an Arham complex. I can write this as Arham, but I don't see why it should be complicated. So we can have an Arham complex, like that. Then we can take the cohomologies of that Arham complex, and we'll get these groups. And in fact, we can show that there is a complex of vector bundles, where the vector bundles are these cohomology sheaves. And this, I'm writing down that complex of vector bundles, which resolves that complex. So I will discuss about resolution to this deformation obstruction complex. So let's just write this down as this omega C over S twisted by this divisor D, O of C over O of Sn. O of C tensored over O of S with N. Okay. Now, what does the brilliant think? As I said, it has to do with this definition, that this thing is a perfect complex. So Li and Tian prove that this tangent obstruction complex is perfect in the sense of definition 8, which I just put in here. This means that there exists a two-term complex of vector bundles. This is essentially what I just said there, but I was already using the result. So this is due to them. So there is a two-term complex of vector bundles. E1 goes to E2 such that the structure sheaf of these EIs, these are bundles, geometric spaces, they define sheaves, are given by those sheaves. So these are cohomology sheaves. Remember that as I was saying, these are cohomology sheaves of some Arham complex. You have some Arham in the derived category, you take the cohomologies of it, those give you cohomology, sheaf cohomologies, right? So these give you sheaves. Okay, and then you will get this thing. Fiber-wise, over the points of the modular space, the map between these two things is 0.
Sorry. I think I'm getting. So you have like the map of differentials, and you also have the E1 and E2.
Yes. I have map of differentials. Yes.
And for the two-term complex, the two sheaves are the cohomology groups of the map of differentials.
Yes, that's right. So I'm just saying there is an object in the derived category whose cohomology sheaves are basically given by this. And that's right. And that object in the derived category has a resolution by a two-term complex of bundles. So think about moduli space of sheaves. The moduli functor has tangent obstruction functor. And then the moduli functor, this is defined for the functor. Now the moduli functor also has the nice property that is represented by a scheme. That's the moduli space. On the derived category of the moduli space, there is some object of the derived category. That's R-HOM F, F. That's the universal sheaf parameterized by the moduli space. And that R-HOM F, F has cohomologies. If you take care of automorphisms for your sheaves, make them stable and so on, the moduli scheme doesn't see those, because stable sheaves always have C star automorphisms, right? But then on the level of coarse moduli space, the coarse moduli space doesn't see that after you fix the stability. So you will have a Deligne-Mumford stack, actually a scheme. Okay, now on this scheme, you have this R-HOM complex. Take the cohomologies of it. Turns out that only two cohomologies are non-vanishing, depending on the dimension of the scheme. Let's say dimension of the underlying variety is 3. This is what, yeah, I should have said. I'm doing this for 3-folds, which is the usual thing. Okay, well, we can do it for surfaces. We can do it for 3-folds. Let's say we have a 3-fold, which is a smooth projective. Now we have x0, x1, x2, and x3. I have gotten rid of the automorphisms, and we have Serre duality. X0 and x3 are gone. We have only two non-vanishing cohomologies, x1 and x2. But when you take the cohomology of this R-HOM complex, you don't get groups, right? You get sheaves, right? You get x1 sheaf and x2 sheaf on your moduli space. Fiber of these two sheaves on every point of the moduli space literally give you deformations, the first order deformations and obstructions to those deformations at that given point of the moduli space. Now the idea is that this R-HOM complex that we have defined, this is some object in the derived category. And there is another object in the derived category of this moduli space, which is given by a complex of vector bundles. And this complex of vector bundles is perfect of two-term and resolves this one. This is for the sheaf story. Now we are doing this for the stable map moduli space. I find it always easier, maybe at least for me, the thing for the moduli space sheaves, but so. Okay, so this is that. Now that we have something like that, of course, this is proven by Li and Tian. It's non-trivial. It's a major progress in maybe the most major progress in the cohomology theory. So, and they did it first, and then we will also discuss about Behrend and Fontecchi construction. So then, from here, then they construct, then the authors, then Li Tian, construct a Kranich map. Kranich map F. So this is important. How is this Kranich map defined? It is E1 hat or something to E2. What do I use? Upper, yes. E1 to E2, like that, where, so, how is it? Fine, so E1, where E1 hat is the formal composition, is the formal completion, and I know that you guys are very familiar with this terminology, of E1, but if not, tell me, of E1 along its zero section. So out of a map of vector bundles E1, E2, one of which understands the deformation spaces at every point of the moduli space, the other one the obstructions to those. You construct another map of bundles, first one of which is the formal completion of the bundle along the zero section. Okay? Okay. Now on each point, by construction, on each point, let's call that P of the moduli space. Now this object lives in the derived category of a scheme that represents the moduli functors. You see, now I'm using the straight M's. On each point of this algebraic space, the zero locus of the map F of F is the formal completion of M bar Gn x beta at P. This is not so surprising. And in other words, the zero locus of F is formally isomorphic to the completion of n Gn x beta, maybe I write it like this, to the completion M bar hat Gn x beta of M Gn x beta times M Gn x beta along its diagonal. In particular, F gives an embedding of mgn x beta into formal completion of this bundle in formal completion of E1 inside along its zero section. Now I claim that if you didn't understand this blackboard, when I talk about Behrend and Fontecchi, you will understand it, then you will be sure that you understand this blackboard too. Think about what does it mean, sheaf of differentials of a scheme. Okay, so for this bit, think about this. You have some embedding of x inside y, and define relative differentials of x and y or normal bundle of x and y. What is that? Right? Think about the map, the diagonal map that embeds x inside. And you have some ideal. So the conormal sheaf of x inside y is, so the conormal sheaf of x inside y is given by pull back of I mod I squared, where I is a module over here. Think about this picture if you want to understand this one. In some sense, yeah. That's okay, so then now consider this is the very geometric way of defining this. This is what is called virtual normal cone and things like that, which were studied later much more algebraically by Baron and Fontaine. This is pure due to Lee and Tien. Now consider cone, the normal cone of this completion work. And in fact, the intrinsic normal cone or the virtual normal cone, in fact, the virtual normal cone is the restriction of this cone to m bar x, m bar gmx. What is going on? You have m bar gmx beta. You have the formal completion of this. You have the bundle. Okay, so this you have this bundle in here, and you have the normal cone of m bar with respect to the completed bundle over here. So this normal cone goes inside, and it lives on here. You pull back this thing to there. That is what you would call virtual normal cone. Okay? So C of E dot lives on m bar gn x beta. It's embedded inside this thing, which lives on m hat bar. This is m hat bar x beta. And then goes inside E1 hat. That's what the virtual normal cone is. Now remember that by now the Kronishii map, which was giving us a map from this formal completion of E1 along 0 section to E2. We can see that we get an embedding of this guy inside E2. We obtain
What is E2?
E2 is the obstruction bundle. We obtain an embedding CLB1 inside E2. And then get an embedding in here. And remember that this bundle also lives on the moduli space, so this bundle lives on m bar gmx beta, and this is the 0 section on E2. So all I need to do is to pull back this via the 0 section. So then the class of this, of course, the class defined by this. So maybe I should say this guy has dimension equal to rank of E1. then the virtual class of n bar g and x beta is given by 0, the pullback of the class of this thing by the 0 section of it. As you can see, because this thing has dimension equal to rank of E1, when you pull it back via the 0 section, it's the dimension of the class that you obtain in here will be, the degree of the class you obtain in here would be rank of E1 minus rank of E2. That's exactly the expected dimension. So this is the geometric way of looking at the virtual fundamental class. This is the original story, which came before Artan and Fontecchi story. By using the theory of using the coordination theory. Okay, now, Artan and Fontecchi construction, on the other hand, is kind of different, but it has many, many similarities and many similar flavor to Litian story. So let me just do that too. So brief summary of Artan and Fontecchi construction. Of virtual fundamental class. So what is it they are saying? So they are saying since M bar G and X beta, I mean, I'm applying their construction to the marginalized space of the stable maps. They did it for general schemes, but I'm applying already. So this, since this has an atoll covering, since this has an atoll covering by schemes, and sorry. This is stack. The marginalized functor, which is the same as the stack. It has an atoll covering by schemes, and one can then work locally then. And one can work locally over schemes, let's say U, and embed. So M is covered by schemes, UI, so we are working on one of those things, and embed this scheme U inside an ambient to smooth thing. So embed U inside W, which is a smooth. So their construction is via this, okay, so you have a covering of your marginalized by the schemes, you locally take these things, embed them in an ambient smooth thing, via this embedding, define a normal cone construction, then glue the normal cones, you will get the intrinsic normal cone of all marginalized space, then do this. That's basically what it is. And gluability of these normal cones and the cycles is directly related to the fact that obstruction theory of your marginalized space is perfect. If it is not perfect, you will need to add extra structure to your marginalized space, some homotopy theoretic structure to your marginalized space. This was also worked out at the time I was a student. Weiland, Chan, and was it them? Yeah, I think so. John. Semi-perfect obstruction. Yeah. Okay, so you have that. So you can embed this inside something smooth. Now let we are embedding a U inside W, so that has a canonical short exact sequence. So this is the ideal of embedding U inside W. This is a local thing for UI. It's like one of those local things. So algebraically speaking, the normal cone of U in W, now that we have this idea of defining the embedding, is given by the affine spectrum of ik mod ik plus 1. Okay. And so in fact, via the differentiation map, so differentiation map, which sends I to shift of differentials of omega. How does it do it? F goes to df. Take the derivative. We did this last time. Then this differentiation map induces a map of algebras, induces a map of algebras. So it sends this guy to symmetric kth algebra of omega 1 restricted to modulo pi times omega 1. Now if you take the spectrum of these two things, the spec of this is a surjective map. You take the spec of this, and that, and so what is this? This is the tangent of W restricted to U, and that is the normal cone of U inside W. We did this. So those things that are purely supported on U, because this is the ideal of U, so if it vanish along, you can go away. For the work is supported on U. Okay, so since then this is because we are writing it in here for the sake of completeness. This is the spectrum of k equal to 0 infinity of symmetric kth algebra of 1. Yes, it's true. So there exists a notion. There exists a notion of quotient stack, which actually during the past 2 sessions we did here and there talk about it. Quotient stack, and the intrinsic normal cone. Normal cone is defined as the stack quotient. This is important. The stack quotient of normal cone of U and W by this guy. You have a map from here of this bundle as acting on this guy. So for every element of this, the action is defined via moving it by the map. Okay, so that element of that plus f. The map is called f of some element here. So this acts on that, and then you can take the quotient in the stacky sense of c with w with respect to this. Intrinsic and the normal cone, intrinsic normal cone is defined by this stacky quotient. All you need to do is to glue these normal cones to each other over the whole modulizers. Okay, the normal cone. Cone is independent of choice of W, which implies we can glue them to each other. We can glue them all to each other. For all such U. If you look at the paper of Barrett and Fantecchi, you can see that there are some couple pages to prove that this is an independent of choice, and this is beautiful. There it is. Glue them to each other over such U and give intrinsic normal cone of the modulation. Okay. Note that the way that we locally constructed this cone was by taking the affine spectrum of all of these normal symmetric algebra of normal sheets. So basically, note that this guy is generated by summing by I1 over I2, right? And so, in particular, there exists an embedding. Oh, sorry. There exists a surjection from K, the sum of K symmetric algebra of I1 by I2 to this fact. Take all of these things and symmetrically multiply and put elements in here, and that's a surjective map. So you take the spec of this thing, and it injects inside E. But what is this thing? You can do this again locally for such U, and then show that the object that you will get in here, well, we already show that these are giving us cones and they glue to each other. They're independent of choice of W. Same thing in here, but this is the normal sheaf. This is the normal sheaf of U inside W. So this gives us intrinsic normal sheaf. This is intrinsic normal cone. Okay, so if you give me a moduli space, if I can compute this intrinsic normal sheaf for my moduli space, I can immediately see that the normal cone of the moduli space inside some ambient bundle is going to be embedded inside it. And I can use that to construct the virtual class. Now, by Lucy M has a cotangent complex. complex where
Sorry, what is your
M? M for us is the moduli space. The moduli stack of stable maps into an ambient variety.
I mean, shouldn't there some property of your N in order to have your cotangent complex?
No.
No?
No.
Arbitrary scheme has a cotangent complex. I mean, assuming material is
Yes. If it is even a stack,
Even a step.
yeah, if this is smooth, the cotangent complex only has one term. It sits in degree 0. And that's the shift of differential. If it is non-smooth and a Deligne-Mumford stack, you embed it inside an ambient, smooth thing. And you will obtain a cotangent complex, which is restriction of the shift of differentials of the ambient guy. Let's say you have something Deligne-Mumford into here, you embed it inside here, you will have a complex for this, which is the restriction of shift of differentials of this to x, and then it has many other terms. So for the first minus one term is the co-normal shift of this embedding, and it has more and more terms. It could go from 0 to all the way to minus infinity. And you know, if it is other things, for instance, it could be an Artan stack, then it will have a term in degree 1. If it's an Artan quotient stack, at least. Quotient by some group scheme. It will have some, so this has term in degree 0 and all the way to minus infinity. It's a quotient stack, for example, Artan stack, which is a quotient stack. It has some term in here. Let's say if x is something like this, where this is non-smooth, it's quasi-projective scheme which is non-smooth, divided by some group scheme in the stacky sense. Then, still you can embed x, but then the cotangent complex of this stack has something in degree 1. And that's the dual of the Lie algebra of your G. Tensor with all x. What I can say is that the quotient stack has a cotangent complex where you can pull it back to x and see what it is, and the pull back has this description. So as you see, I'm writing a structure sheet of x, not something like a structure sheet of the stack, but it's things in the upstairs stuff. The cotangent complex is fine. It could have infinitely many terms. So where H0 of this L dot of M gives deformations, and H minus 1 of this L dot of M gives obstructions. Obstructions, the obstruction theory, the deformation obstruction theory then, obstruction theory of M is given by a map in the Drives category, a homomorphism in the Drives category of M. So it's given by something like E dot to L dot of M. Such that let's call this map mu. H0 of mu is an isomorphism, and H minus 1 of mu is an epimorphism. So this deformation obstruction theory or deformation obstruction complex is the one that we defined in the previous blackboards today, where I was saying that there exists some complex in the draft category of the scheme, if it exists, that represents the moduli function. You see, the difference, so there's no reason to be confused in here. The cotangent complex of the moduli space understands the first order deformations of points parameterized by the moduli space, obstructions to those deformations, but then obstructions to obstructions and obstructions to obstruction to obstruction, and it will go all the way to minus 2 infinity. The deformation obstruction complex that we have been talking about today, the two-term complex, only sees two of these terms. So what is special about this deformation obstruction complex? It's a nice two-term approximation of the full data of deforming the points parameterized by the moduli space. And in what sense is it a good approximation? In the sense that, at least in the deformation level, it gives us the exact same deformations, but then it is cooked up in a way that it has bigger obstructions. So this map is an surjection, and somehow it doesn't have other terms. It has a locally free resolution by bundle. So basically over here you can see the way that often people cook this up is that it has bigger obstructions, and that obstruction sheaf induced by this guy, it would become a bundle. And it wouldn't jump in dimension, so. And this is essentially the thing that you need to do calculations and to define integrals. You don't need a full cotangent complex. So even if you truncate this cotangent complex in degrees bigger than -1, so make it a two-term thing. Of course, truncation, cohomological truncation, doesn't leave this a perfect complex, but that's fine because this is supposed to be a perfect two-term complex. So that's why often when people write it, they write it as a map in the derived category from some nicely cooked up complex to a truncation in degree -1 to and above of the full cotangent complex. Okay, so that's that. And another virtual class. So if you have something like this, if E dot is this complex, if the E dot is a complex. Now, okay. Also, remember that I kind of confused you a little bit by saying that this is always perfect of two-term. It might not be, but we can always cook up a perfect two-term complex out of this. So how to do that? This is that statement. If E dot is a complex of arbitrary length, complex of arbitrary length, like this, E -1 for instance, F E0, E1, E2, that, for instance, we can define H1, H0 of dot of Picard stack of dot. This is called the Picard stack. Well, this is not a Picard. Is it? Is this also Picard stack? Okay. Nothing. So I give a definition of what this is. This is the stack quotient of kernel of G by co-kernel of F. If this complex satisfies these properties, then H0 and H -1 has these properties. We use it and we define the stack quotient like that. Okay? And we can show that, and we can also show that this is the Picard stack. So the Picard stack of the cotangent complex of dual of the cotangent complex is the intrinsic normal sheaf. Remember that the intrinsic normal sheaf was defined by taking the stack quotient of the normal cone by the restriction of tangent bundle of the ambient smooth thing. So you can actually see it in here, right here. Remember that he just asked this question. So the degree 0 and -1 terms of L dot, this is a complex which is quasi-isomorphic to I mod I squared divided by some omega W like that. So now dualize it. This is the conormal sheaf. This is the conormal of U in W. Conormal sheaf of U in W. If you dualize it, you will get exactly that thing, and you will get the normal sheaf of U inside W. And that's exactly defining an action of tangent bundle of W restricted to U on this. We take the static quotient. This is exactly that. Now what is the point? The point is that if you have a nice approximation of the cotangent complex, you have two quotient stacks. One you obtain from here, one you obtain from here, and there's a map obviously between them because of the original map in the draft category between the deformation obstruction complex and the cotangent complex. So that gives you what you want. So basically, then since you have this, then you will get that in the dual level. You just take R hump with O of the moduli space. This defines this map. This defines the dual deformation obstruction complex. Then this induces map H1, H0 of L dot M dual into H1, H0 of E dot dual. The fact that this is an injection can be seen by the fact that in the H minus 1 level, this map is a surjection. Okay? Okay, so this gives you a map like that. Okay, so, wait a minute. Yes, so remember, what was this thing? This was, and the normal cone, we know by what I just said, because the algebra of normal cone is generated by the algebra of the normal sheaf after taking the spec, the normal cone, also that's inside here. And I'm not writing U's and doubles anymore because here I'm assuming that we have glued them all together. It's an abundant of choice. So what's the final picture? The picture is that we have, so E dot dual, let's say, has this E dot, has E minus 1 E0, say. E dot dual has E0 dual acting on E minus 1 dual. And this is defined by taking the static quotient of this via the action defined by this. So you will get a diagram like this. H1, H0, E dot dual, which is in the sense of the stacks, E minus 1 dual quotient is by E0 dual. You can easily define what this quotient stack means by evaluating as a functor. It's a stack, it's a two functor. Evaluate it and you will see what its definition is. And so this has intrinsic normal sheaf of M in it, and has intrinsic normal cone of M in it. Now, we will take the fiber product of C of M, fiber product over H1, H0, E dot dual, is 1, 2. And this defines an embedding. And this defines an embedding inside. So then M virtual will be by definition the new image of view intersected with zero section E minus 1. Which is again, this is the E minus 1 dual, this is the obstruction bundle basically. E minus 1 dual in here. So it has zero section, and you know, it's always the same as Konishi theory. You have this moduli scheme, moduli stack. Locally, you think of it as a scheme, not a smooth maybe, embedded inside ambient, a smooth thing. Construct a cone, complete it, construct a cone, think of this cone. So you will get this cone embedded inside the zero, inside the obstruction bundle. The cone of your moduli space embeds inside formal completion of the obstruction bundle along its zero section. And then you can actually intersect it with the zero section of that obstruction bundle. The same Li and Tian theory was exactly the same thing, and this is a little bit more out of the way. But this, for me, at least for my taste, is more understandable for some reason. Maybe it's because I'm more familiar with this. But anyways, it's really very, very similar in flavor. Any other questions?
When you say this is more understandable, partly because of your background, but for me, it seems if everything has to go to this elusive quadratic complex, it becomes very abstract. And unless in your particular problem, you know how to go to after truncation, you know how to.
I'm not at all claiming that. I understand all the things that Illusi wrote, but I just understand tiny parts of it. But yes, that's right. It's very hard text anyway. But maybe for you, this Li and Tian description is much more understandable.
Concrete, I would say.
Yeah, from a Konishi point of view, I did that before you come. So if you look at the videos, in the first hour of the class, we just discussed about construction of virtual class using Konishi. You always think of your moduli space as a zero locus of the Konishi map. Locally construct the virtual cycles, and then use the fact that again these cones and so on that you use, these are gluable to each other. So you can do it globally over the whole modulus.
And also, so from your lecture, so you say so that moduli stack has no constraints. So any reasonable moduli stack has a built-in conjecture complex, not like Lucy. And then you have all this. So as long as you are given a moduli functor, there's always a built-in tangent abstraction theory associated to it.
Yes, yes, but then not every tangent obstruction theory is useful. It needs to be perfect. Tangent obstruction theory just means that you have the map in the derived category, and it needs to satisfy isomorphism in the H0 level and epimorphism in -1 level. But the perfectness is the main issue. Because these are bundles. These are cohomologies of a complex in the derived category. These are bundles associated to cohomology sheaves of a complex in the derived category. And we need to show that these sheaves are locally free globally. The perfectness of the obstruction theory actually doesn't give you that. If this thing doesn't have that property, then there is absolutely no difference between E dot and L dot. Then none of these are, constructible. This is a quotient stack of a bundle by an action of another bundle. It needs to be bundled. Yeah, so that's how it depends on finding the perfect obstruction period.
It's an important point.
Yes, it's very important. Derived geometers do this in a different way. Derived algebraic geometers do this in a different way. They find the right enhancement of the moduli space to a DG moduli space. And they use the quotangent shift of that DG moduli space as the object that induces the perfect obstruction.
You mentioned this a year ago, but I never had time to.
I was going to actually do that this semester. I wanted to do the derived geometry because I'm right now using it for my own research. I'm very curious about it. So on.
Sorry, can you ask it a bit more? So when you work with the DG setting, What do you do again? You
So if you have moduli stack,
Sure.
then you find the right DG enhancement of it,
Sure.
DG moduli
Sure,
stack.
sure.
And then that ambient thing is obviously smooth.
Sure.
If you can find such nice thing,
Uh-huh.
then that's a cotangent sheaf.
Right.
The pullback of its cotangent sheaf has a map to the cotangent complex of your moduli stack.
Uh-huh.
And that some drive stack whose pullback of tangent sheaf or pullback of whose tangent sheaf is this deformation obstruction. This was already written in some of the notes by Bertrand Towen and Timo Shorik and Keith maybe. And this actually gets related to many other the industry of this drive algebraic geometry becomes actually very useful when you work with situations where from the beginning, even the very obvious canonical deformation obstruction complexes are not going to be perfect. Like if you just change, he asked the question and I was making an example with the perfect obstruction complex of moduli specific sheaves on a threefold, which after getting rid of automorphisms has only x1 and x2. That's nice, that's perfect. This thing would be a complex of perfect two-term complex. If you just increase the dimension of the variety no matter what, and if you still look at the stable sheaves, your complex which has more terms. If you get rid of automorphisms and they're dual, still it has 3 terms. Then what can you do? Now you need to use full throttle machinery of drive technology. Okay, so next time I will do some examples for the virtual fundamental class of quintic and things like that, computations, and then after that we just move to calculation of Gromov-Witten invariance and we slowly start talking about quantum cohomology. Thanks so much. Any other questions? And interestingly enough, the battery of this thing died away some time ago.